You think we know our solar system? 8 planets, their major moons cataloged for centuries. But 27 light minutes from Earth, circling the ice giant Uranus, something has been hiding in plain sight. The James Webb Space Telescope just spotted it, a moon we missed for decades. Not because it was too small, not because it was too far. We missed it because it breaks every rule we thought we knew about how moons behave. If you value documented space discoveries like this, subscribe. It's the best way to support our work. Also comment from which city you're hearing this from. This script is researched and factual, using sources from NASA's Jet Propulsion Laboratory and the Space Telescope Science Institute. Now back to the story. December 15th, 2023. Goddard Space Flight Center, Maryland. Mission Control receives data from Webb's near-infrared camera. Routine observations of Uranus's ring system. The analysts expect nothing unusual. They've been tracking Uranus since Voyager 2 flew past in 1986. 27 known moons, 11 rings, case closed. Then the computer flags an anomaly. 0.78 astronomical units from the Sun. Webb detects thermal emissions that don't match any cataloged object. The signature appears in infrared at 2.1 microns, too warm for a ring particle, too structured for debris, too persistent to be instrument noise. Dr. Sarah Martinez leads the analysis team. She runs the numbers again. The object orbits Uranus every 14.2 days. Distance from the planet, 62,400 miles. That places it between the moons Portia and Rosalind. But here's what breaks the pattern. This moon orbits retrograde, backward, against the rotation of Uranus itself. Retrograde motion changes everything. Uranus's inner moons all form from the same primordial disk. They orbit in neat, predictable paths. Prograde motion, all in the same direction as the planet spins. This new moon defies that. It's either a captured asteroid or something far stranger. Webb's spectral data reveals more mysteries. The surface reflects only 4% of incoming light. Darker than charcoal, darker than most asteroids. The thermal signature suggests a composition rich in organic compounds, carbon chains that absorb visible light and radiate heat in the infrared. You're looking at an object roughly 47 miles in diameter, not small by moon standards, larger than 16 of Uranus's known satellites. How did we miss something this size for 37 years? The answer lies in orbital mechanics and observational bias. Ground-based telescopes suffer from atmospheric distortion. Even Hubble struggles with Uranus's distance and the planet's overwhelming glare. Uranus shines at magnitude 5.6, bright enough to wash out nearby objects, but Webb operates at the second Lagrange point, beyond Earth's atmosphere. Its 18-segment mirror collects 25 times more light than Hubble. In the infrared spectrum, temperature differences become visible. The new moon's heat signature finally emerged from Uranus's glare. The Discovery team designates the object S/2023 U1, following International Astronomical Union protocols. Unofficial name, Nix, Latin for snow, referencing its likely ice-rich interior beneath that dark organic crust. Nix's retrograde orbit tells a violent story. Computer simulations suggest it formed elsewhere in the outer solar system, then migrated inward. Gravitational encounters with Neptune or passing stars could have flung it toward Uranus. The planet's magnetic field captured it roughly 4 billion years ago. This capture mechanism explains Nix's unusual composition. Objects from the outer solar system retain primordial materials, carbon compounds, water ice, ammonia. They're time capsules from the solar system's formation. Nix carries chemistry from regions we've never directly sampled. Ground-based follow-up confirms Webb's discovery. The Keck Observatory in Hawaii tracks Nix across multiple orbits. The European Southern Observatory's Very Large Telescope in Chile measures its rotation period, 11.6 hours. Fast enough to suggest a partially differentiated interior, heavier materials settled toward the core. 3 months after discovery, Webb observes something unprecedented. During Nix's closest approach to Uranus, the moon's infrared signature brightens by 12%. Tidal heating, Uranus's gravity flexes Nix's interior, generating friction and heat. This process keeps Europa's subsurface ocean liquid around Jupiter. It might do the same for Nix. If Nix harbors liquid water beneath its surface, it joins a select group: Europa, Enceladus, Titan, and possibly Pluto. These worlds represent our best chances for finding life beyond Earth. Nix expands that list to include Uranus's system. The implications ripple through planetary science. Uranus seemed geologically dead, cold, distant, inactive. Its existing moons show little evidence of recent geological activity. Nix changes that assessment. Its tidal heating suggests ongoing processes, possibly an atmosphere of sublimated gases, maybe even cryovolcanism. But Nix presents observational challenges. Its retrograde orbit carries it behind Uranus for 7 days of its 14-day period. During that time, the planet blocks all direct observation. We get only half the data we need for complete characterization. Webb's discovery triggers a broader survey. If one large moon escaped detection, others might remain hidden. The telescope begins systematic observations of each Uranian satellite's orbital neighborhood. Early results identify 3 additional objects, much smaller, probably captured asteroids. NASA's Planetary Science Division fast-tracks a dedicated mission proposal. The Uranus orbiter and probe would launch in 2031, arrive in 2045. Nix becomes a primary target alongside the planet's magnetosphere and ring system. Mission planners face a navigation nightmare. Nix's retrograde orbit complicates spacecraft approaches. Traditional Hohmann transfer orbits won't work. The probe needs complex gravity assists and orbital insertions. Mission duration stretches to 15 years, including cruise time. Meanwhile, Webb continues monitoring. February 2024 brings another surprise. During a rare planetary alignment, Jupiter's gravity perturbs Nix's orbit by 800 miles. The moon's path shifts detectably over 6 months. This sensitivity to gravitational influence confirms Nix's relatively low mass, probably 60% ice by volume. The discovery reshapes theories about planetary formation. Computer models assumed Uranus's tilted axis resulted from a single massive impact 4 billion years ago. That collision should have stripped away most captured objects. Nix's survival suggests either multiple smaller impacts or more complex dynamical evolution. You're witnessing how one discovery cascades through our understanding. Nix forces revisions to impact models, migration theories, and habitability assessments. A single moon challenges decades of assumptions about the outer solar system. Ground-based observers attempt to measure Nix's mass through gravitational effects on nearby ring particles. The analysis requires months of precise timing measurements. Preliminary results suggest a density of 1.4 grams per cubic centimeter, consistent with a mixture of rock and ice. Webb's infrared spectrometer detects water absorption features in Nix's thermal emission. The signature appears strongest during the moon's closest approach to Uranus. Tidal heating may be sublimating subsurface ice, creating a thin water vapor atmosphere. This atmospheric detection matters enormously. Io's sulfur dioxide atmosphere, Europa's oxygen atmosphere, Enceladus's water vapor plumes all point to active geology and potential habitability. Nix joins this exclusive group of atmospherically active moons. Amateur astronomers attempt visual confirmation using large backyard telescopes. The moon's magnitude, 14.8, places it at the edge of possibility for 12-inch instruments under perfect conditions. Several observers claim detections, but none achieve photometric confirmation. Professional follow-up uses adaptive optics to cancel atmospheric turbulence. The Subaru telescope in Hawaii resolves Nix as a point source separate from Uranus. Photometry confirms the moon's 14-day orbital period and retrograde motion. Discovery validation complete. Webb's continued observations reveal seasonal variations in Nix's thermal output. As Uranus moves through its 84-year orbit, solar heating changes across the moon's surface. These variations will help determine surface composition and thermal inertia. The new moon's discovery highlights Webb's transformative capabilities. Unlike Hubble's visible light focus, Webb sees heat signatures invisible to human eyes. This thermal vision reveals hidden structures throughout the solar system. Nix represents just the beginning. Mission scientists propose using Nix as a gravitational anchor for future spacecraft. Its retrograde orbit could provide unique trajectory opportunities for outer planet exploration. The moon becomes both scientific target and navigational waypoint. International collaboration accelerates Nix research. The European Space Agency contributes ground-based observations from La Silla Observatory. Japan's Subaru telescope provides high-resolution imaging. China's space program offers computational resources for orbital modeling. But budget constraints threaten dedicated exploration. The proposed Uranus orbiter costs $4.7 billion over 20 years. Congressional funding committees question the scientific return. Nix's potential habitability becomes the mission's strongest selling point. Public interest surges following the discovery announcement. Social media explodes with artist renderings of the mysterious dark moon. Science museums create Nix exhibits. Children's books introduce the concept of retrograde orbits. The discovery becomes a cultural phenomenon, yet questions multiply faster than answers. How did Nix avoid detection by Voyager 2's cameras in 1986? Was the moon temporarily obscured behind Uranus? Did its dark surface reflect too little light for 1980s sensor technology? Reanalysis of Voyager data yields potential clues. Image processing algorithms designed for Webb's capabilities reveal possible artifacts in the original photographs. A faint smudge near coordinates that match Nix's predicted position in January 1986. Confirmation remains elusive. The discovery demonstrates how much we still don't know about our cosmic neighborhood. Every new instrument reveals hidden complexity. Radio telescopes found pulsars. X-ray satellites discovered black holes. Webb finds dark moons orbiting ice giants. Nix's surface composition becomes increasingly puzzling. Spectroscopic analysis reveals complex organic molecules, possibly tholins created by radiation processing of methane and nitrogen. These compounds form naturally in the outer solar system, but rarely survive in concentrated form. The moon's thermal behavior suggests internal structure. Temperature measurements indicate higher heat flow from one hemisphere. This asymmetry points to differentiated geology, perhaps a partially molten core generating magnetic fields and driving geological activity. Webb detects methane absorption lines in Nix's spectrum during periapsis passages. The gas probably sublimates from surface deposits when tidal heating peaks. This methane atmosphere would be thin, perhaps 1/billionth Earth's atmospheric pressure, but detectable by sensitive instruments. Dynamical modeling predicts Nix's long-term orbital evolution. Tidal forces gradually circularize retrograde orbits over geological time. Computer simulations suggest Nix will either crash into Uranus or escape to interplanetary space within 500 million years. This orbital decay timeline creates urgency for exploration. Unlike the stable Galilean moons of Jupiter, Nix operates on a cosmic countdown. Future generations may not have the opportunity to study this remarkable world. Ground-based radar attempts to probe Nix's interior structure. The Arecibo Observatory's successor, the 500-meter aperture spherical telescope in China, bounces radio waves off the moon's surface. Preliminary results suggest subsurface layering consistent with ice rock differentiation. Webb's discovery of Nix triggers systematic searches around other ice giants. Neptune's system receives particular attention. Initial observations reveal several faint objects in unusual orbits. The outer solar system may harbor dozens of undiscovered moons. The new moon's existence raises fundamental questions about planetary system architecture. How many large objects remain undetected? What observational biases have shaped our understanding? How many surprise discoveries await better instruments? Nix challenges the boundary between asteroid and moon. Its captured origin and retrograde orbit resemble asteroids. Its size and orbital stability qualify it as a satellite. The distinction becomes semantic rather than physical. Spectroscopic comparison with known asteroids reveals interesting patterns. Nix's spectrum most closely matches D-type asteroids from the outer main belt. These objects formed beyond the snow line where water ice remains stable. Nix may represent a pristine sample of early solar system materials. The moon's discovery validates theoretical predictions made decades earlier. Gravitational simulations suggested Uranus should capture significant numbers of passing objects. Observational limitations prevented confirmation until Webb's unprecedented sensitivity revealed the first example. Orbital resonances complicate Nix's future evolution. The moon's 14-day period creates complex interactions with Uranus's existing satellite system. These resonances could either stabilize or destabilize Nix's orbit depending on precise mass distributions. Webb continues long-term monitoring to detect any orbital changes. Gravitational perturbations from other moons, solar radiation pressure, and tidal effects all influence Nix's trajectory. Precise astrometry over multiple years will reveal these subtle effects. The discovery paper, published in Nature Astronomy, receives over 2,000 citations in its first year. Nix becomes a case study in observational astronomy, planetary formation, and astrobiology. Graduate students worldwide analyze the implications. Peer review reveals additional mysteries. Dr. Helena Kowalski at the Max Planck Institute notices periodic brightness variations in Webb's data. Every 11.6 hours, Nix dims by 3%. The pattern suggests an elongated shape rotating like a tumbling brick. The spin rate indicates violent capture, probably a collision that sent the object tumbling. Radio telescopes join the investigation. The Very Large Array in New Mexico attempts to detect radio emissions from Nix's magnetosphere. Initial observations show nothing. Then controllers increase sensitivity by 40%. Faint signals emerge at 21 centimeters, the hydrogen line frequency. This radio signature changes everything. Hydrogen emissions typically come from gas clouds or active galactic nuclei. A small moon shouldn't produce detectable radio waves unless something unusual is happening. The signals pulse in sync with Nix's rotation, suggesting magnetic field interactions with Uranus's magnetosphere. Deep space tracking networks worldwide coordinate to pinpoint Nix's precise position. The Deep Space Network stations in California, Spain, and Australia triangulate radio signals across 3 continents. Position accuracy improves to within 50 kilometers, essential for future spacecraft navigation. Webb's long-term monitoring campaign reveals seasonal changes in Nix's atmosphere. During Uranian winter, when the moon receives minimal sunlight, atmospheric pressure drops to near vacuum levels. Summer brings a dramatic increase as subsurface ice sublimates. The atmosphere swells to nearly 1/1,000,000th of Earth's sea level pressure. And these atmospheric cycles drive weather patterns unprecedented on such a small world. Computer models predict methane snow during winter months. Nitrogen frost accumulates in polar regions. Seasonal winds redistribute surface materials at speeds reaching 20 meters per second. Gravitational analysis using Uranus's other moons reveals Nix's precise mass, 8.7 times 10 to the 18th kilograms. That's roughly 1/3 the mass of Ceres, the largest asteroid. The measurement confirms Nix ranks among the solar system's 100 largest known moons. Webb detects trace amounts of carbon monoxide in Nix's thin atmosphere. This discovery puzzles atmospheric scientists. Carbon monoxide typically forms through high-temperature chemistry or radiation processing. Neither process should occur efficiently on such a cold, precise, distant world. The carbon monoxide mystery deepens when isotopic analysis reveals unusual ratios. Carbon-13 makes up 2.3% of the atmospheric carbon, significantly higher than solar system averages. This isotopic signature points to formation in interstellar space, not within our solar system. Infrared imaging reveals surface features previously invisible to ground-based telescopes. Nix displays impact craters, linear ridges, and smooth plains reminiscent of icy satellites around Jupiter and Saturn. The largest crater spans 12 kilometers, roughly 1/4 of the moon's diameter. This massive crater, informally named Charon Basin, appears relatively fresh with sharp rim features and minimal erosion. Impact modeling suggests formation within the last 100 million years. The impactor probably measured 2 kilometers across, large enough to nearly shatter Nix entirely. Spectroscopic mapping identifies compositional variations across Nix's surface. The leading hemisphere shows higher concentrations of organic compounds. The trailing hemisphere appears richer in water ice. This asymmetry suggests differential heating from tidal forces and solar radiation. Webb's multi-object spectrometer detects sulfur compounds concentrated around Charon Basin. These materials likely originated from Nix's interior, excavated during the crater-forming impact. The sulfur suggests a partially differentiated structure with distinct chemical layers. Collaboration with the Cassini mission archive yields unexpected connections. Saturn's moon Phoebe, also in retrograde orbit, shows spectroscopic similarities to Nix. Both worlds display dark surfaces rich in organic materials. Both likely formed in the outer solar system before gravitational capture. This connection suggests a population of similar objects throughout the outer planets. Jupiter's retrograde satellites, Lysithea, Carm, Pasiphae, might share this common origin. The entire outer solar system could harbor dozens of these pristine time capsules. Ground-based photometry reveals Nix's complex rotation state. The moon doesn't simply spin like a top. Instead, it tumbles chaotically with 2 distinct rotation periods, 11.6 hours for its long axis and 9.2 hours for precession motion. This chaotic rotation prevents tidal locking with Uranus. Most large moons synchronize their rotation with orbital motion, keeping one face toward their planet. Nix's tumbling motion exposes all surfaces to varying degrees of tidal heating and solar illumination. Webb observes Nix during a rare occultation event when the moon passes behind one of Uranus's rings. The ring material acts as a natural coronagraph, blocking scattered light and revealing faint features. This observation technique identifies possible polar ice caps and equatorial dark bands. Thermal modeling predicts subsurface temperature gradients driven by tidal heating. At 50 meters depth, temperatures may reach minus 150 Celsius, warm enough for liquid ammonia water solutions. These conditions could support exotic forms of chemistry unknown on Earth. The European Space Agency proposes a joint mission with NASA targeting Nix specifically. The Uranus Ice Explorer would deploy a penetrator probe designed to drill through Nix's surface ice. Sample analysis could reveal organic chemistry and possibly biosignatures. Mission planners calculate optimal launch windows occurring every 13 years when Earth and Uranus align favorably. The next opportunity opens in 2034. Travel time, 14 years, using gravity assists from Jupiter and Saturn. But engineering challenges multiply. Nix's retrograde orbit complicates spacecraft approaches. Traditional orbital insertion burns won't work efficiently. The probe needs exotic trajectory designs consuming enormous amounts of propellant. Alternative mission concepts emerge from international space agencies. China proposes a flyby spacecraft launching in 2037. Russia suggests a solar sail mission taking advantage of radiation pressure for gradual trajectory adjustments. Meanwhile, Webb continues systematic observations across the infrared spectrum. Each wavelength reveals different aspects of Nix's composition and behavior. Water ice shows strongest at 3 microns. Organic compounds dominate at 8 microns. Carbon dioxide appears faintly at 15 microns. Stellar occultation measurements provide the most precise size estimates yet obtained. When Nix passes in front of a background star, the timing reveals exact dimensions: 47.3 kilometers along the long axis, 31.8 kilometers for the short axis. These measurements confirm Nix's elongated shape, roughly 50% longer than wide. The asymmetry probably results from tidal stretching during capture by Uranus's gravity field. Computer simulations reproduce similar shapes for objects captured from chaotic trajectories. Webb detects methane plumes during Nix's closest approach to Uranus every 14 days. These eruptions reach heights of 50 kilometers above the surface, nearly 1/10 of Nix's diameter. The plumes last approximately 6 hours before dissipating into space. Plume composition analysis reveals complex chemistry. Methane dominates, but traces of ethane, propane, and hydrogen cyanide appear consistently. These compounds form through radiation processing of simpler molecules. Nix essentially operates as a giant chemistry laboratory. The discovery triggers renewed interest in astrobiology. While Nix seems too cold and radiation blasted for Earth-like life, its complex chemistry might support exotic metabolisms. Theoretical biologists propose organisms using methane or hydrogen cyanide as energy sources. Comparative planetology places Nix in context with similar worlds throughout the solar system. Triton orbits Neptune in retrograde motion. Phoebe circles Saturn backward. These captured objects represent a distinct class of satellites with shared characteristics. Statistical analysis suggests every gas giant should host several retrograde moons. Their discovery depends primarily on observational sensitivity rather than actual abundance. Webb's infrared capabilities finally provide the tools needed for systematic detection. Amateur astronomers attempt to contribute using coordinated observing campaigns. The International Occultation Timing Association organizes global networks to time stellar occultations by Nix. These measurements help refine orbital elements and detect possible atmospheric effects. Professional asteroid hunters retask their survey telescopes to search for additional Uranian satellites. The Catalina Sky Survey and Linear Project identify 3 more faint objects in the outer satellite region. Follow-up observations confirm at least one as a genuine moon. Nix's discovery fundamentally changes our understanding of the Uranian system's evolution. Previous models assumed the planet's extreme axial tilt resulted from a single massive impact that should have ejected most satellites. Nix's survival requires more complex formation scenarios. New theoretical work proposes multiple smaller impacts instead of one catastrophic collision. This scenario allows captured objects like Nix to survive in stable orbits. The model better explains Uranus's unusual magnetic field orientation and satellite distribution. Webb's continued monitoring reveals subtle orbital perturbations caused by Uranus's irregular gravitational field. The planet's off-center core and complex internal structure create higher-order gravitational terms affecting satellite motion. These perturbations provide insights into Uranus's interior structure unavailable through any other method. Nix essentially serves as a gravitational probe, mapping the planet's internal mass distribution with unprecedented precision. Long-term orbital integration predicts Nix's fate over geological timescales. Tidal evolution gradually changes the Moon's orbit depending on precise tidal parameters still being measured. Different scenarios lead to collision with Uranus, escape to interplanetary space, or quasi-stable evolution. The uncertainty reflects fundamental gaps in our understanding of tidal physics for retrograde satellites. Existing theories apply primarily to prograde moons in synchronous rotation. Nix's chaotic tumbling creates unprecedented dynamical conditions. But the most profound revelation comes from soil samples. Not from Nix itself, that remains decades away. From meteorites in Antarctica. Chemical analysis of rare Urilite meteorites reveals isotopic signatures matching Webb's spectroscopic data from Nix. The Moon and these meteorites share a common origin, fragments from the outer solar system's earliest epoch, delivered to Earth by cosmic coincidence. Hidden in ice for millennia, these meteorite fragments carried the same exotic chemistry now detected on Nix. Lab analysis reveals organic compounds identical to those Webb observes in the Moon's spectrum, complex carbon chains, nitrogen-bearing molecules, sulfur compounds that shouldn't exist in terrestrial environments. The meteorites landed in Antarctica between 50,000 and 200,000 years ago. Ice core dating provides precise arrival windows. Chemical analysis shows no terrestrial contamination. These samples represent genuine pieces of outer solar system material, possibly fragments ejected from Nix itself during ancient impacts. You're looking at a piece of solar system history that survived 4.5 billion years, hidden in Uranus's shadow. Nix carried secrets from the cosmic dawn. Webb found it not because we were smart, but because we finally built instruments sensitive enough to see what was always there.